Hi, guys, and welcome to our next discussion, or our ongoing discussion about protein folding kinetic or about kinetics. Um, Remember the last time we spent some time thinking about um, this simple kinetic scheme, or we dipped our toes in thinking about the quantitative descriptions of kinetic behavior by thinking about a process like this, where we have A, substance A turns into substance B. You guys remember this has an associated rate constant, symbolized by that lowercase k, right? And I showed you that the temporal behavior with which A turns into B, or A disappears, B appears, is readily described by this um, relatively straightforward rate law um, that describes a unimolecular process like this, in which we have the change in the concentration of A as a function of time is simply equal to the amount of A we start with times an exponential function of time where the rate constant K multiplies our independent variable there, time, right? Really pretty straightforward. And out of this, we get these nice, simple sort of exponential decay plots, function of time and concentration of A, right? Okay. And we went on from that and we said, well, okay, that basically assumes that the rate at which B turns into A is zero. Never happens. It's a one-way, it's an so-called irreversible unimolecular process. Remember, unimolecular is distinguished from second order or bimolecular processes by only having one substance, one thing turning into something else. And bimolecular process, second order, which we also talked about last time, you have a slightly different form of this equation. But in this case, we had this irreversible unimolecular process. All right. But I also talked about, how that irreversible process sometimes is a good description or a completely accurate description of a process. A lot of times it's not, right? So we talked about the case where we have to think about the idea that A turns into B with this forward rate constant K sub 1, but we also potentially have to think about B turning back into A with this reverse rate constant K minus 1, right? So-called a reversible unimolecular process. But I sort of took an easy way out. We said, well, if we assume, assume we have a process like this and we assume we're at equilibrium, things get kind of easy, right? Because then we just find out that the equilibrium constant is simply equal to those ratio of those rate constants, which would be K1 forward over K minus 1 if we define the equilibrium constant as product over reactants, right? Which is just then equal to concentration of B over concentration of A. Now that's great, except for the problem that in most cases, when you're trying to understand something about the mechanisms of a system that has kinetics associated with it, studying that system at equilibrium, unless you're looking for thermodynamic parameters, is not so useful, right? If the whole point is to understand kinetics, well, at equilibrium, you have no kinetics, right? So the idea here, or the issue we have to grapple with, is what do you do with the simplest possible system, a unimolecular system, where we want to understand the kinetics, and we can't assume all this stuff about equilibrium? What if this doesn't apply? What if we fundamentally are thinking about a unimolecular system that is reversible and for which we cannot neglect that um, uh, reverse rate constant, right? Where that guy is significant. Okay. Now, this is a little bit more complex case kinetically. Turns out the behavior is relatively straightforward to understand, but to understand where this comes from, we have to sort of grapple with this a little bit, right? And to make this a little bit less abstract, I want to sort of turn back to something we've already been talking about, which I slipped up on the beginning of the lecture with, and that's thinking about protein folding. I'm going to go back to thinking about protein folding a little bit. Now, less as a kinetic, thermodynamic problem, but now as a kinetic problem, right? So in this case, we would have sort of our unfolded state, right? Our unimolecular conversion. Then let's assume it's a simple protein. Globular protein folds in essentially a single step, no intermediates, folds in the native state. We have our forward rate constant, which I'll call K sub F, right? And remember, if we had a protein that was so biased towards the native state that we could neglect the reverse rate constant, this process would model single exponential kinetics, right? We would have the concentration of the unfolded state as a function of time, which is equal to the concentration of the unfolded state at time 0 times e to the minus kt, right? If we had a process that was unimolecular, right? Okay, but again, the whole point of what we're going to do now is thinking about what do you do if that's not true? What if you also have a protein that's not as biased to the native state, and this is not at all uncommon, that you now have to think about the rate of unfolding of that protein. Even if, Kf is bigger than Ku, if Ku is significant, you can't ignore it anymore. And this results in some distinctive kinetic behavior when the unfolding rate constant does not equal 0, right? And when Kf is not much greater than Ku, right? When they're sort of in the ballpark of each other. Now we have a slightly more complex problem to deal with, right? And the kinetics no longer behave the way you would predict for a simple single exponential decay, right? The shape of the curves actually does, but the magnitude of your important constants in the equation don't anymore. And to illustrate that, before we dive in, let's look at it this way, right? So here, let's think about that process, right? We just talked about it. I sort of gave you a hint. If we consider we have a folding reaction, it's unimolecular, here's some simulated data. Here is sort of the loss. So I've created some simulated. There's that exponential decay. That's what the shape of that curve would look like, right? And there's a fit, that decay looks great. We can, of course, think about the native state folding, same way. Start over here at 0. We don't have any to begin with. Remember, this is a kinetic experiment. We're starting with sort of 100% of the unfolded state, and then we do something to trigger folding, like we have it denatured, and we use a stop flow to rapidly dilute out the denaturant. And now we're going to watch U turn into N, right? So there's the 100% of U to begin with, and it disappears, or there's no native to begin with, and then the protein folds. All right, so you can do this. There's that single exponential. We, of course, say, I wonder what the folding rate constant is, so we would fit that. In the case of a unimolecular folding reaction like this, we would use, for the disappearance of the unfolded state, it's a decreasing function, right? So it's that straightforward single exponential. Have to modify that equation slightly if we're thinking about the folding, right? It's basically a 1 minus, right? You guys may remember that. Again, it's the same basic functional form, but you sort of have to add that 1 into the expression. And then you can beautifully model the folding state, the folding rate. And out of this, you should get exactly the same rate constant, right? The unfolding, the loss of the unfolded state here, and the rise of the native state governed by the same basic exponential term, and that rate constant should be the same. You see, it's, in this case, because I made it up, it's right around 2 per second. All right. What happens now if we can no longer neglect the unfolding rate constant? What if it's not huge, so the protein's still going to fold, but it's no longer insignificant? It's not ignorable. This is no longer correctly modeled as an irreversible single unimolecular process. All right, here's what happens. Here's that process again. There's the unfolding rate constant. Now I've added to the kinetic description of the system a unfolding rate that's small. It's not huge, but it's not insignificant anymore. Look what happens, right? You'll notice that in the case of the unimolecular process, with the same folding rate constant, the value I've used here is exactly the same. notice something. Notice the amplitude is no longer the same. Even though KF is the same for both of these data sets, the full drop doesn't go as far anymore. Well, both of these data sets are fit to a single exponential functional term, and they both fit pretty well, right? If you did the formal analysis, it looked like a great fit. But check this out. In this case, remember, KF, right, the folding rate constant was 2 per second. The K observed you would get in this case is now almost twice the folding rate constant, the true folding rate constant, and it doesn't equal the value of the folding rate constant. So in this case, with a reversible step, the amplitude decreases here, right? The amplitude here is smaller than it was for the single unimolecular step, right? And the rate constant, the observed rate constant, appears is bigger, which means the process appears to be going faster, even though what's going on here is we've added in a reversible step to this same process. Now, why that's the case, you can't really understand until you get a look at the rate law that comes out of a description of this process. So buckle up. That's what we're doing next.